Okay, so we shall go through quickly the last lecture first of all and then go to the next lecture. So in the last class we discussed about the normal approximation, right? Normal approximation. So these are very commonly used model actually. Normal distribution is a mathematical model. There is no real life situation where some random variables data exactly fits a normal distribution. Right? So, but for most of the situations, there are a lot of situations where this model approximates the actual distribution of some random variable. So it is also called Gaussian distribution. It's also called bell-shaped distribution because it has a bell shape. But you have to remember that there are other bell-shaped distributions also. So not only the normal distribution has bell shape. For example, there is a distribution called T distribution. That is very similar to a normal distribution. Right? It has a bell shape. But some properties that exact normal distribution has are not in those distributions. Right? So the shape itself doesn't allow you to choose a non-normal model. Therefore, you have to check other things also if you want to choose a normal model for the actual distribution of your data. So I'll come to that a little later. Okay, yeah. So this is the mathematical equation of the normal curve, right? And it's a little bit complicated, but it's a bell-shaped curve. So it's a function of x here. Mathematically, it's a function of x, where x can be anything between negative infinity and positive infinity. And in addition to that, there are two quantities inside the equation. One is denoted by mu, and that is actually where the distribution is symmetric, right? The distribution is symmetric around whatever the value mu. For example, if we have 5 here, then this distribution will be symmetric around the value 5. And this value is the one which controls the spread of the distribution. Right? If this number is a large number, then the distribution has a large spread. If this number is a small number, then it has a small spread. So therefore, this value here is called the location parameter. Right? That is where the distribution is located, actually in the center. And this one is called the scale parameter. But we can also show that if a certain population, we use this normal distribution for the actual distribution of the population of some random variable. In that case, this mu will be the mean, population mean, and this sigma will be the population standard deviation. So we can interpret those numbers therefore in two ways. One is the location and the scale, right? The parameter that controls the center and the parameter controls the spread. In another way, we can say this is actually the mean, population mean, and this is the population standard deviation. But of course, we don't have the data for a population always. Therefore, usually we don't know the value of mu and value of sigma. So what we usually do is when you have a sample of data, when you draw the histogram, for example, if it looks like approximately bell shape, then one possible model is the normal model. There are other possible models as well, but one possible model is the normal one, and that is the one usually we try first. Right? So in that case, we take the sample mean as an approximate value for this, and the sample standard deviation will be used for this. Right? So when you substitute sample mean here and sample standard deviation here, so this becomes a function of x. Right? So in that curve, if the normal distribution is a suitable model for that situation, then the curve given in that situation should be a good approximation. That is one thing. So I have shown you that several normal distributions, and I explained, like I showed you in the last class, how the value of mu and value of sigma controls the location and the spread. Right? And I told you that there is a one particular important distribution, that is when mu is equal to 0 and sigma is equal to 1. That is called the standard normal distribution. Standard normal. Right. The area under any of these is actually 1, or as a percentage is 100%. Right. So all of these curves have the same area under the curve. Right. So standard normal distribution is a very useful one for us. So that is this distribution. Actually, for any normal distribution, not only for standard normal, for any normal distribution, there is a one particular property. This property is not in other bell-shaped distributions. Like T distribution doesn't have this particular property. That is, if you look at the area between mu minus sigma and mu plus sigma, if you consider mu minus sigma and mu plus sigma, right? So these are two values, and the area under the curve, not on the standard normal, actually I am considering here the usual normal distribution with mean mu and sigma standard deviation. So if you consider that kind of normal distribution, in this interval, roughly 68% of the data, otherwise it is two-thirds of the data is going to be between these two values if the data fits a normal distribution. Right? One thing is it has to be a normal bell-shaped curve, another thing is approximately symmetric around the value mu. Right? And then sigma is very difficult to find out directly, so you have to check these conditions. For example, if you have such S standard deviation, you use standard deviation here, then you can find out x bar minus s, right? Because you don't know mu, you put x bar in the sample. You use the standard deviation for here, so you can find out x bar minus s and x bar plus s, and you can find out how much data as a percentage between those two in your data set. Right? So if the normal distribution is a good fit, roughly 68, not exactly, roughly 68%, so it can be 70, 67, 65, or that around those values. That is one requirement. There should be roughly 68% of the data in your data set between x bar minus s and x bar plus x in a data set, roughly. And then if you consider mu minus 2 sigma and mu plus 2 sigma, within this interval, 95% of the data should be there. And if you consider mu minus 3 sigma or mu plus 3 sigma, so in a data set this will be x bar minus 2 times s, x bar plus 2 times s, and so on. So you can find out those two values, because you can find out x bar, you can calculate from the data, s also you can calculate from the data. So therefore you can find out this interval, and then you can find out how many observations in the data set in that interval. So if the normal distribution is a good fit, these three should be approximately satisfied. Right? 68, roughly 68% of the data should be between these two numbers, 95% of the data should be between these two numbers, and almost all the data should be between these two numbers. Right? So those are the requirements for you to check whether a normal model is suitable for a given data set. Okay, so if you consider the same idea for the standard normal distribution, then what do you say? Mu in this case is 0, sigma is 1, so therefore roughly 68% of the data should be between -1 and positive. Roughly 95% of the data should be between -2 and +2. Actually, this particular distribution, it happens like that. Right? Theoretically, it happens like that. And then between -3 and +3, 99.7%. That is theoretical fact. Right? So what we do is we check whether that theoretical fact is correct for our data if you want to use a normal model. So this property sometimes called empirical rule. Right? For any normal distribution, this rule is valid. So in the book they have shown some examples where the normal distribution can be used as an approximation for the actual distribution. So for example, here the women's height from one survey. So this is the histogram, and so we can draw a curve like that approximately. So, but this, just because it is a normal looking or bell-shaped curve, we cannot say whether actually a normal model is suitable. For example, T distribution, there is another thing called logistic distribution. They all have that kind of shapes, right? So if a normal model is suitable, then you have to check whether these three conditions are also satisfied, at least roughly. Right? So for this data set, for example, they have found out that the X bar value, average is equal to 63.5 and the standard deviation was 3, right, from the data. So then we can check what percentage of data are between X bar minus S and X bar plus S. So they have checked that one. They have seen that between those two values, approximately 72% in the data set. So theoretically it has to be, if it is a normal distribution, 68%. But this is not very far away, no? So therefore it can be considered as approximately correct. And not only that, actually you have to check these two also, but they have not checked that one. If you check that one, I think it will be probably correct also. If that is the case, then it is reasonable to assume that the data have a normal distribution. Then we think that the data are normal distribution. And then once you assume that the data are normal distributed, then we can use that model to answer a lot of other questions. So you only find out the model using the data. You have to only know the X bar and mu and then check these conditions. So if you think that the normal model is suitable, then after that a lot of theory can be applied to answer a lot of other questions. So but here they don't talk about that kind of things. Here just they're talking about how to use the how to get the normal approximation, right? So now if a random variable say X has a normal distribution. Now if you think that, because after checking those things, if you assume that X random variable like height in this previous situation, X has a normal, so this is the usual notation. X follows a normal distribution, and then within bracket you should write down those numbers mu, and here we write down actually sigma square, that is not the sigma, right? So for example, in the previous case, if you use the same notation, if you think that X has a height, right, in this case height, so I'll use H for height, for example. So H has a normal distribution with mean 63.5, and this quantity is actually the variance, right, the square of the standard deviation. So the standard deviation is 3, so this number has to be 9. Right? So we will usually write down like that. H height has a normal distribution with mean this number and variance this number. So once you know the variance, you know the standard deviation. Right? So that's how you usually denote it in short. Right? So if some random variable has generally a normal distribution with mean mu and some variance sigma square, then if you consider this transformation, say Z is equal to X minus mu over sigma. So that is a linear transformation. If you subtract the value mu from all the X values and then divide all those values by sigma, you get new values. Let's call those new values Z. And theoretically, we can show that Z has a normal distribution with mean 0 and variance 1. Theoretically, we can prove that if X has a normal distribution and if Z is given by this linear transformation, then Z also has a normal distribution, but the mean will be now 0 and the variance and the standard deviation both will be 1 in that case. So that means Z has a standard normal distribution. So that is how you convert any normal distribution into a standard normal distribution. Right? The use of that is actually, as I told you in the last class, in order to find out the probabilities or the proportions of observations within given two values, we use standard normal tables. Right? So that is the main use of this thing for us. Right? Once you convert this thing, this quantity will not have unit. For example, suppose x is in centimeters heights, right? So then x is in centimeters, mu will be in centimeters, sigma is in centimeters. So therefore z will not have any units. So those actually are, those are just numbers. They are called standard units, right? It's not centimeters or kilograms or whatever. It's called standard units. So this is the formula that we will be using to convert any x value into a standard unit if x has a normal distribution. If x has a normal distribution. Okay, so z value then will give you some idea about how far away your x value is from the mean in terms of standard deviation. How many standard deviations above the mean or how many standard deviations below the mean your x value is. Right? For example, when you calculate z value using some x value, suppose you get 2.5 here, 2.5. So that means your x value is 2.5 times standard deviations above the average of x values. If z is equal to 2.5, that means your x value is 2.5 times the standard deviation of that those data, right, above the mean. If you get a negative value for this thing, then that means your x value is below average, that many standard deviations below the average. Right. So when you, for example, now you know we use this formula to calculate z scores also. Right. In that case, data are not normally distributed, right? But still we can calculate this quantity, no problem. In that case, if usually the marks of lot of subjects are not normally distributed, right? So therefore z will not be normally distributed in that case. So z scores are not normally distributed. Many people, even lecturers and professors, some professors think that this is used to convert data and marks into normal distribution. That is completely wrong. Right? Many people don't know. So they think that they are using this to convert your marks, make the marks normal distributed. That's completely a wrong idea. But anyway, if you calculate z values using this thing, still the other meaning, the idea, that is how many standard deviations above or below you are, for example, your mark is from the average marks for that class is given. Like for example, if your z value for some subject is 2, that means you are 2 standard deviations above the marks of that subject. 2 standard deviations of that subject above the mean. If your z value is negative 1 point something, then you are below the mean, that means standard deviations. So what they do is actually for each subject they calculate z value separately and then take the mean. Right? So that cannot be directly interpreted like that because it's a mean of those things, but for individual subjects you can interpret z value like that. But remember, just because you are using this formula, the distribution doesn't become normal law, standard normal law, anything. Right? Z will be normally distributed only if x is normally distributed. Otherwise, Z will not have the same, Z will not be a normally distributed. Right. So here they have used, they have shown some examples. For example, for the previous example, 69.5, if somebody's height was this value, then when you calculate the standard units, you get 2. So that means this number is 2 times standard deviation, 2 standard deviations above the mean, right? This is the standard deviation. So 2 times standard deviation is 6. So this number is 6 points above the mean. So that's very simple. So I showed you in the last class, right? When you, this is the original scale, right? In that case, this is the density, original density, but you can convert all those numbers by taking away the mean and dividing by the standard deviation. You can convert this axis into the standard units by using that formula. Right? So for example, this number will be converted into 0 because this number minus the same number divided by 3. This number becomes 1 because this number minus the mean, this number divided by 3 becomes 1, and so on. So the same can be used using standard units. In that case, the density height will be different. So the density of the standard normal density, height of that will be sigma times the height of the original density. Right. So in this case, it is 3. So therefore, this scale is 3 times that. Right. So we use this table usually to find out the area under the standard normal distribution. Remember, this is for only the standard normal distribution, but practically we don't have to, we don't need to only to find out the area for the standard normal distribution. Practically we have to find out areas for other normal distributions. So what we do is first, for example, if you are told, if say you are assuming that x has a normal distribution which say mean equal to 50 and say standard deviation equal to 10, and therefore the variance is 100. Right? Suppose you want to find out what is the percentage of x's, right, between say 40 and 60. What is the percentage of data between 40 and 60? If you assume that x has a normal distribution with mean 50 and variance 100. So what you do is you convert both of these numbers into Z. So here this will be, I call it Z1. Z1 will be 40 minus 50 divided by 10. Remember to divide by the standard deviation, not by the variance. And the other value will be converted into Z2 is equal to 60 minus 50 divided by 10. So this is -1, this is positive. So you can find out now, instead of finding area between this and this for under this normal distribution, now what you do is to find out the area between -1 and +1 under the standard normal distribution. So that can be actually in this case found directly because it gives you the area between any z value and negative z and positive z. But on the other hand, suppose you wanted to find out here area between 40 and 70. So in that case, this number will be 70 and this number will be 2. Right. So now you cannot directly use this one, but in the last class I showed you how to do it. Is there any problem there? I think it's very simple, right? You can do it. Yeah. So that's how you usually do it. Right. So if you think that the data have a normal distribution after checking the previous conditions, see whether it's symmetric around some value, so take that as your middle value, mu value, and then find out the standard deviation, take that as sigma, and then check whether the empirical rule is approximately satisfied. If that happens, then you are okay to assume that the data are normally distributed. If that kind of situations, actually that normal model is well described by the mean and the standard deviation only. So only two statistics is enough to explain for the whole distribution, right? Because once you know mu and sigma, you know the whole model. Once you know the whole model, you can answer any question, you can find out probability and so on. But if you cannot assume, if it is not reasonable to assume that the data are normally distributed, right? As I told you, even if it has a bell shape sometimes, the empirical rule may not be satisfied. If the empirical rule is not satisfied, then you cannot assume it is normal. Maybe it is some other distribution. Right? But mainly, if the data are not symmetric, for example, if they are skewed and so on, of course, definitely you cannot use a normal distribution. In that case, that means the mean and standard deviation itself is not enough to describe the data, because you cannot get the shape of the distribution of a skewed distribution using the mean and standard deviation only, right? So in that kind of situation, if you want to describe the shape, right? If you want to describe the shape, for example, here you have the histogram of income of people in 2004. So definitely this is, in this case, the normal model will not be suitable at all. Right? But still, if you want to describe this distribution using some numbers, one thing you can do is you can talk about the percentiles instead of the mean and the standard deviation. Mean and standard deviation will not be enough to describe this whole shape. Right? So in that case, usually people mention about percentiles. Percentile, for example, 10th percentile, 20th percentile, 30th percentile, 40th. If you want, you can talk about 41st percentile, 45th percentile. So whatever the percentile means, a value on this axis. Right? So that means a value for your random variable, value for your data, below which p% of the data will lie. For example, if you say 30 percentile, that means you are finding out a value on this axis below which the total area will be 30% of the whole area. Right. So you can find out that using your data itself or using the histogram. Right. If you have the data set, of course, you can find out below what number 30% of the data lie. Right. So that will be the 30th percentile. Like that. So in this case, they have obtained those data, those percentiles using the data. So the 10th percentile is equal to $15,000 means in this particular sample, 10% of the people had income less than or equal to 15,000. 50th percentile is 54,000. That means 50% of the people have income less than or equal to $54,000. So like that, we can talk about percentile for any value, any percentile, first percentile, second percentile, 10th percentile. But there are three very important percentiles. For example, 50th percentile. If this is the 50th percentile, so that means the total out of total observations, 50% of the values will be less than that. The other 50% will be above that. So therefore, this 50th percentile is the same as Q2, the second quartile, or it is the same as the median. Right? So 50th percentile, Q2 and the median all are the same. Right? And if you can find out some value below which which is the 25th percentile. So below that value, there will be 25% of the data. So if that is the 25th percentile, so that will be the Q1, first quarter. And if you can find out some value, say 75th percentile, so below that, there will be 75% of the data. So that will be our Q3 usually. So those are three special percentiles. Q1, Q2, Q3, this is also the median. So this distance, right, is called interquartile range. Interquartile range. So within this distance, therefore, again, this is 25% here, 25% here, and then 25% here, and then 25% here. So therefore, between this and this, 50% of the data. So that is actually the range of the middle 50% of the data. Middle 50% of the data, and this quantity is usually used as a measure of the spread of the data when the data are skewed, when the distribution is skewed. Right. So that's the end of the last lecture actually, those things. Any question in that one? I think that one is not difficult at all, right? It's very easy to understand. So now let's go to the new chapter called measurement error. Right. So in this case, we are talking about observations that we are getting by measuring something. Measuring. When do we get observations by measuring? For what kind of variables usually we get the data by measuring? Numerical, right? Numerical, not only numerical actually. For the discrete data, usually we get the data by counting, usually. Counting is a number of things, usually. We get the observations by measuring, mostly for continuous data. So therefore here mainly we are talking about measuring some continuous variable, right? Obtaining some observations. Now suppose you are measuring some fixed item, it has some length for example, or something with a fixed weight. Now consider taking observations, not only one measurement, several measurements under the same conditions. Several measurements of the same item under the same conditions as much as possible. Sometimes it may not be ideally possible to have the same, exactly the same condition, but as much as possible, let us assume that we are controlling all the other things around that. We are using the same method, right? Room temperature is the same, atmosphere pressure is the same. Anything that can influence the value are the same. Right? We are using the same instrument, probably same person is doing the thing. Right? So even if we do like that, usually there are differences between the observations. No matter how careful we are, no matter how precise our instrument is, right? If you are taking observations of the same unit again and again and again repeatedly, usually this is the usual phenomenon. Observations are going to be not exactly the same. There will be some variation of the observation, some variation. Now this variation that occurs is usually called the chance error. Chance error. So there is some value that actual value that, for example, if we are measuring a weight, for example, so there is an actual weight. We don't know the value. Right? If we knew the value, we don't have to measure it. Right? So there is an unknown actual value. When we observe that, we get a value, maybe that unknown observed value plus a little small number, or maybe it minus a little small number. So this number that it can be going above the actual value or below the actual value. We don't know when we, for example, suppose we don't know in a given situation whether we are above the actual value or below the actual value, because we don't know the actual value. And if you repeat this experiment of measuring the same thing, we don't know. For example, suppose without knowing to us, we were little above the actual value. The next one, whether it will be above or below, we cannot say also. So that's completely random. So therefore, usually there is a difference between the actual value and the observation, even if we use very precise measurement instruments to measure the weight, for example. So in that case, there is something called, this is called due to chance error. Some people call random error. or chance error. So it can be positive or negative quantity. Yeah, usually not very large, usually it has to be small, but if you are very carefully, precisely measuring it, but still there will be difference. If for example the measurement instrument also has some kind of error, right? In that case, in addition to the chance error, there will be another part added or subtracted. This part is usually always fixed, right? It is coming because of the instrument's problem, not the random error, right? So therefore, in general, if you talk about in general, the possibility is observed value will be equal to the actual value plus some quantity, fixed quantity, plus a random quantity. The fixed quantity can be again positive or negative, but if it is positive, it is always positive when you are taking a measurement of 1 unit. If it is negative, it is always negative when you are taking repeated measurements. So that quantity is fixed, but that fixed quantity can be positive or negative in a given situation. The random quantity can be positive or negative in anywhere. We don't know whether it's positive or negative in a given situation. So therefore, generally, we can write down a model like this. Observed value will be the true value plus the fixed quantity is a systematic quantity, that is called the bias, plus the chance error. So bias is a systematic, it is always the same. Systematic means always the same, doesn't change. This quantity can be going above or below 0, right? Positive or negative. So together, this quantity is called the measurement error. So generally, when we take an observation, observed value is equal to true value plus some measurement error. Right? Measurement error can have a bias, or maybe it doesn't have a bias if everything is okay. Instruments are also very correct and so on. In that case, there will be no bias. In that case, only the chance error. Right. So bias is a constant offset that shifts all results in one direction always, in one direction, but it can be positive or negative. For a given experiment, it is positive always, or for a given experiment, it is negative. Chance error is a random quantity, can be positive or negative. Generally, if you consider large number of observations, the chance error of these observations will cancel out generally. But if you have a small number of observations, of course they may not cancel out. In that case, there may be some residue remaining when you get the error. Of course, this error and bias we cannot directly observe. Right? We can observe only get only the measured value, observed value. But that quantity contains the true value plus the bias and the random error or the chance error. So I have created a picture to explain it further, but I think this is also already clear. Suppose, for example, you are measuring something like some length, fixed length. Suppose its actual length is 10 centimeters or something. Right. Suppose due to an error in the measuring tape or something, suppose always we get something additional to that. For example, if the tape is stretched, right, we will have something additional to the actual value as our measurement. Right. For example, if the actual length of a meter in our tape is 37 inches, but we will be, it's recorded as 36, right? So when we read 36, actually we have 37. So actual observation is actual plus value plus 1, right? So like that. There can be a positive bias, the bias will be the same, and then on top of that there will be a random quantity. So here I am considering several measurements, for example. So for the first observation, actual value is this one, and the bias, and then the random error in this case is negative. So finally my observation will be this value. That will be my observation. So in that case, my measurement error will be the distance between this and this. If you consider this one, then this is the true value and this is the bias, and then there is a positive chance error also. So my observation will be here, therefore the measurement error will be from here to here, all length. So these are my observations and these will be the measurement errors. If you have a negative bias on the other hand, the picture is like this, maybe this is the true value and there is a negative bias, and then on top of that there is a chance error. Right. So I have given few examples taken from the book. One example in the book is a fixed standard weight. That weight is called NB10. That is the name of that object. So it is supposed to be standard 10 gram. It's supposed to be standard 10 gram. So people have measured the same item 100 times. I think even more than that, but the book has, I think, 100 values. So you can get the values from the book, but I have written down only the first 5 values that they got. So actually these numbers, by looking at, you can see they are all less than 10. Actually, if you look at all the other numbers, they are also less than 10. So these are the observations. In this case, actually, they knew that there was no error in the measuring equipment. Measuring equipment was, they are sure that there is no error there. Right. So in this case, actually, there is no bias there. There is no bias. What has happened is actually, even though they thought that the actual weight was 10 grams, the actual weight is actually not 10 grams, it is less than that. We don't know the actual weight. Right. So what we have here is that therefore, whatever the actual weight which is less than 10, plus or minus some other quantity, random quantity. Right. So you can see that up to 3 decimals they are the same, but after that the numbers are different. So instead of looking at these numbers, what they analyzed was the difference between this number and 10, right? So they have subtracted this number from 10, so that gives you how much below 10 each of these observations were. Right? So they have data like this. They observed, right? All the observations I have shown you only the first 5 numbers. So you can see that these are somewhat above 400, below 400 and so on. So they look like they're somewhat around 400. These are going to be micrograms because these are the last 6 out of 6 numbers, last numbers. So what has happened here is actually this is a situation where the observed value is actual value or the true value plus some chance error, where we don't know this one, and therefore because we don't know this one, we don't know this one also, but the model that is suitable for this situation is this one, because there is no bias, there is no explanation for bias, because they knew that the measurements were, instrument was correct, there is no error in the instrument. Usually the bias occurs because of the measuring in instruments. Right. So that is a situation where there is no bias, but still the chance error is always there. Right. There is another example where in Sri Lanka I think we have this kind of situation very much, not only the butchers everywhere. Right. Suppose a butcher is a steak with his thumb resting on the scale, right? Now, not only this, they have raw scales also, usually in Sri Lanka. Right? This introduces a consistency in every measurement. Right? So, if you put your fingers always, that's going down a little bit. So, that actually introduces a bias. Always that amount is there. If you put in your finger always there. And then on top of that, when you measure in the same steak, but there will be some variations due to some other reason. Usually the reason for this random error or chance error is unknown. Right? We don't have explanation. That occurs anyways. Right? No matter how careful we are, No matter how much accurate the measurements instrument is, always there is some variation. Right? So that is called the chance error. Usually people think that the chance error is occurring not only because of one reason, maybe large number of unknown reasons. Right. So in this case, therefore, you can model your data, observed weight as true weight plus a bias introduced by putting the thumb, and then chance error. So similarly here, another one that can occur when you're measuring some length of a cloth using a tape, for example, cloth tape. Right? So this is an example. If the 36-inch tape has been stretched up to 37, then there will be always a bias, right? Because of the wrong length. That is the problem of the instrument. And on top of that, there will be always a chance error. Right? So therefore, observed length will be true length plus the bias, that is the 1 inch occurring, and then chance error will be there. Right. So the question somebody asked, where do these chance errors occur? Usually the reason for bias can be found because it's a systematic thing. Usually we can find out the reason for bias. But where do the chance error come from? The answer is actually nobody knows most of the situations. There is no explanation how that occurs, but it is observed always there is a variation. Right? And how big are the chance errors? Of course, if the chance errors are small, it's not a problem for a lot of situations. We can still safely use our observations for whatever our purpose. If the chance errors can be very large, if there's a very high possibility of chance error being large, then maybe it is not safe for us to use our data for maybe important decisions and so on. So it's important to have a good idea about the size of the chance error. Even though we don't know the individual errors, right? Individual chance errors, if we can get some idea about at least the average chance error, if we have some idea, that will be a good idea, a good thing, because then we can decide whether we can use, it's okay to use our observations for our purpose or not. Right? And then somebody asked, how likely is to cancel out these chance errors when you consider the average. Right. So the first question already answered, we don't know where these chance errors come from. But the second question, how big are they likely to be? Right. We can find out an answer actually for that. We can show that a typical size, the typical size of the chance error is actually can be obtained using the data itself. Right? So let's see how to get the typical size of the chance error using the data. So actually the book doesn't have this mathematics, but I have included a little bit of mathematics to explain that. Right? What they say is actually the typical size of the chance error is equal to the standard error of the original data, whatever we have. So that's what the theory says. Typical size of the chance error is roughly equal to the standard deviation of the observations that we have. So that's a good thing because we can calculate the standard deviation from the observations. Therefore, we have some idea about the typical size of the chance error. So we can decide whether that chance error is small enough for us or whether it is too big for us. Right. So let's prove that using some mathematics. So this is the model that we are going using. Observed value, say ith observation, observed ith value is equal to the true value that we don't know, plus maybe a bias is there. So let's put it there. Generally there can be a bias. Some situations bias can be 0. But always the chance error will be there. So for the ith observation, let us denote it by chance error subscript I. And suppose we have n observations. So this model is correct for those I from 1 to n. So if I use some mathematics notations, let's denote observed value of I by xi, and then the true value, actual value by a, biased by B. So actual value is a fixed value, it doesn't change with I. B is also a fixed value, it doesn't change with I. It is the same for all the observations. Only the chance error will change with I. From item to item, chance error will be different. So this will be the model in that case. So let's look at now generally if we have some numbers like in this picture. Right. If we have, so these are the chance errors. So if you have chance errors like this, it is around some value. So the typical size of that kind of numbers is given by the standard deviation of those numbers. So if you have some numbers going above or below the average, some average value, then usually we use the standard deviation of those numbers as the typical size. Right? So that is actually the average size. It's not exactly average, but it's a kind of average. It's the average of the square distances from the mean and then taken the square root. So it becomes like something average. So therefore standard deviation is used as the typical size of some numbers when you have numbers around some average. Right. So therefore let's consider find out the typical average. Sorry, the standard deviation. Right. Actually we cannot calculate the standard deviation of the chance errors. We cannot calculate because we don't know the chance errors. We don't know the EI values. We know only XI values. But mathematically we can derive it. Right? So let's consider from the model that we have Xi is equal to A plus B plus EI. So therefore the chance error for the ith observation will be Xi minus A minus B. Right. So EI is equal to Xi minus A minus B. Now, in order to get the standard deviation of we need E bar also because SD of E values will be equal to I from 1 to n EI minus E bar square divided by n and then square root. That is how you define the standard deviation of some number. So for E values it will be like this. Right. So therefore we need E bar first of all. Therefore I have found out expression for E bar. E bar is equal to the average of EI values. So that is sum of EI divided by n. And now I have substituted for EI and then you get this. And that's going to be sum of Xi divided by n, that is denoted by X bar. And then A will be added n times. So n times A divided by n will be A here, negative. And then B will be added n times. So n times B divided by n is B. Right. So therefore E bar mathematically is equal to this one, even though we cannot actually calculate it, we can get an expression for that. So E bar will be equal to this thing. So therefore we can write down the standard deviation of E values using the definition. So I have substituted for Xei and then substituted for X bar. So you can see that A and B cancel out. So finally it becomes this one. So this is actually the standard deviation of X values. So therefore the standard deviation of E values is the same as standard deviation of X values. So that is a good thing. Even though we cannot calculate standard deviation of E values directly because we cannot get E values, we know it is the same as this one, and this one can be calculated from the X values we have. So therefore we can get some idea about the standard deviation of the typical value of the chance errors. And the last question, actually we are not going to answer that question, what happens when you take the average, right? Whether these things cancel out or not and so on. It will be discussed later on in part 7 under chance models. Right? But what we will be looking at there is, now if you want to find out the actual value, why are you measuring these things, for example? Right? Taking several measurements of the same thing is to get the actual value, right? Height or weight or whatever, actual value. So that means, for example, in our model, xi is equal to a plus b plus ei. What we want is a. We want to get the value of a. Right? So, because we cannot get the exact value, what you have to do is you have to estimate it, get an approximate value. And usually what we use as a is, estimate for a is going to be in terms of b plus e bar is going to be x bar minus a. Right? This will be cancelled out when usually not exactly cancelling out, but will be very close to 0 when you take the x bar value. So x bar will be approximately equal to a plus b, and this will be added n times and divided by n. So a will be there. This will be added n times and divided by n. So b will be there. When you add these numbers, usually they will be very close to 0. Therefore, we ignore that. So therefore, x bar will be approximately equal to a plus b. So a will be approximately equal to, x bar will be equal to a plus b approximately. Therefore, a will be approximately equal to x bar minus b. So, yeah, so actually the error in the estimate will be equal to then, our estimate is x bar minus b, x bar minus b. So the error will be, in order to find out the error of the estimate, you have to subtract the actual value. Right? So as I mentioned, error cannot be calculated actually, but theoretically we can get an expression. So we will, in the next chapter 7, we will be talking about how to estimate these quantities. Right? Even though we cannot get the exact value, we can estimate A, and we can get an estimate for the error of the estimate, right? And so on. And that will give you some idea, and then we will look at the likely size of the error, typical size of the error, and so on under this section. Right? What we will see is actually, when you look at the average, the error in average will be usually smaller than the error in the individual values. So here, for example, what will be the error? Xi minus b minus ei, a, right? Error will be xi minus a, right? This is the observed value, this is the actual value, so error will be equal to this thing. So therefore, error from the ith observation will be error I will be equal to b plus ei, b plus ei. Error of the, if you use xi as an estimate for a, if you use xi as an estimate for, because estimate is something that you should be able to calculate. Right? Xi කියන්නේ අපි observe කරන දෙයක් නේ. So we can get a value. So if somebody might use xi as the estimate for the actual value. Right? So then the error of our estimate will be xi minus a. Xi is the estimated value, a is the actual value. So the error will be the difference between those two. So xi minus a is equal to b plus epsilon I. Right? And this error cannot be calculated because we don't know b, we don't know ei. Right? Even though we cannot calculate this one, we can estimate it, and we will look at later on, and we can also estimate how, what is the typical size of that. We can look at that. So that is the error of our estimate, error of our estimate of A if we use individual value as an estimate. And also we can use x bar. X bar also can be used as an estimate for A, because if you write down the model, you have xi is equal to A plus b plus ei. Let's consider the average of I from 1 to n. So this side will be x bar in that case. If you take the average of x1, x2 up to xn. Right? And average of a values will be the same as a. You will be adding a times and dividing by a. So that will be a. And the average of this one will be b. This will be denoted by e bar. So we might use x bar as an estimate also. Sometimes people use x bar as an estimate for A. So in that case, the error of our estimate will be x bar minus A, that is the error, that is equal to B plus E bar. That is the error if you use x bar as an estimate for A. Later on we will show that the error of this quantity, size of this quantity is smaller than the size of this quantity. The typical size of this quantity, this error, is less than this one. Right? If you increase the sample size, this will become smaller and smaller and smaller. Error will be smaller and smaller and smaller. So those things will be discussed later on in chapter 7. Right. Okay. So here in the book they have introduced a new word called outliers. Generally, outliers means the observations which are unusually large or unusually small. Those are called outliers. There are some definitions also in different books, but they are not exactly the same. But generally, that's what we mean by an outlier. Right? If you suppose you have a data set, and generally we know that in almost all data sets, there is a natural tendency that most of the data are centered around some value. Right? That's what you call the central tendency of a data set. There's a general tendency that most of the values are going to be around some value. That is what that value is the one that we usually call the center. Right? It can be usually the mean or the median. So most of the data are going to be around this. So if you look at the distribution, it will be very high around some center. But after that, it will be like this. But still, some observations can be very far away from the center. Oh, here, oh. So those values which are quite far away from the center or quite far away of the bulk of the data, right? Bulk of the data will be somewhere here in the data set. But there will be a few observations sometimes due to different reasons quite far away from the bulk of the data. Then those kind of data are called outliers. So outliers can occur due to several reasons. One reason is naturally due to the natural variation, because the distribution, even though most of the distribution is between this and this, still theoretically the distribution can be quite up to some point like negative infinity, right? So therefore naturally, if you have for example very large data set, one or two can come from the tail. So that observation can look like an outlier. So that is actually not an error or something, it's a natural observation, but it's quite large from the bulk. So in that kind of situation, we call it an outlier. That is naturally occurring due to the actual shape of the distribution. Sometimes, of course, outliers can occur because of errors, right? Recording errors, measurement errors, like that. So that is another reason for occurring outliers. Right? So when you have outliers, what happens? When you have outliers, usually, for example, if you are calculating the mean as your center of the data, it will be affected by this outlier usually. Right? If you have a very large observation, for example, bulk of the data here, but one observation coming from the tail. So when you calculate the mean, what happens? The mean will be tending towards that large observation because we are adding that to the other observations, but again when you divide by n, the average can be quite unusually larger than the usual average. Right? So therefore, that is one problem when you have outliers. Right? So therefore, you have to be careful when you are analyzing the data and selecting suitable summary measures, for example. X bar is not a suitable summary measure for the center, especially when you have outliers. Right? That kind of natural outliers, for example, very large numbers can occur if the actual distribution is positively skewed, for example. Right? If the distribution is like this, right? If you have a large data set, one or two can come from the tail. Right? So they are coming from the natural variation, so there's no problem there. If that is the case, in that kind of situations, we don't usually use the x bar as the average. In that case, probably the median is better than the mean. Right? So therefore, if you have outliers, you have to be careful to first of all see whether it's occurred due to the natural variability or not. That means try to find out whether there is an error, right? Recording error or measurement error or something. If that is the case, probably if you can detect some kind of thing, then probably you can correct it. Right? Or if you cannot correct but still you think it occurred because of that kind of reason, you can remove it before finding out the other things like average and so on. But if you think that is not due to an error like that, if it is naturally due to the natural distribution, then you should not remove that kind of outliers. You should keep it and choose a suitable method to analyze this kind of data when you have, for example, positive. Right? So this is a big important thing actually. Many people, whenever they see this kind of outliers, they just without thinking anything, they just remove it. And then they analyze. So that kind of analysis are not correct always. Right? You have to be very careful, because if it is a real observation, you have to keep that and then choose a suitable method to analyze the data with that kind of things. So therefore it's important thing to understand. Right. So even if, for example, if you go back and look at that 100 measurements that we had of that so-called 10 gram, right? NB10 it's called. So even if you look at that, these are the data. So from the data you can see actually whether there are outliers or not. But if you actually look at the histogram, this was the histogram of those 100 observations. So just for the comparison purposes, they have drawn the normal distribution coming from these data. Right? For example, what they have done is they have calculated x bar and then calculated the standard deviation and then put x bar and x bar for mu and standard deviation for sigma and that curve and then drawn it. So that would be the normal distribution if the normal distribution is suitable. But in this case, of course, you can see that this is not a good model for the histogram. So definitely a normal distribution is not a suitable model in this case. In addition to that, you can see that bulk of the data are somewhere here. So this observation here, one or two observation here, maybe one or two here, can be considered as outliers. Right? They are quite different from the bulk of the data. Right? So if you want to go further and analyze this data set for some other reason, you have to first decide whether you are going to keep these values or not. Right? So they actually checked whether there was any error in the measurements and so on, because this was a very carefully done experiment. Everything, the surrounding area everything was fixed, right? Measured, they are sure that there was no error in the measurement instrument. So therefore, actually, we can think that these observations have actually come from, not from errors, it has come from the real variation, real random error, right? So definitely in that case, normal distribution is not suitable. So you have to think of some other model if you want to use. For example, in this kind of situation, probably you can use something like a T, even though T distribution is not used very much. Probably a T distribution might be suitable, because the T distribution is also similar to normal, bell shape, symmetric around somebody, but it has longer tails. Tails are longer than normal distribution. So therefore, probably a curve like this might be a suitable model. Right? So that has to be done later on. We don't discuss that here, but that is something that I want to explain. Right. So actually what happens is, if you use the normal distribution, you can actually show that not only from this figure, this one definitely doesn't fit, but in addition to that, you can also check the empirical rule also. If you check the empirical rule, what is that? That is, if the data are normally distributed, roughly 68% of the data should be between mean minus sigma and mean plus sigma. 95% of the data should be roughly between mu minus 2 sigma and mu plus 2 sigma. And almost all the data should be between mean minus 3 sigma and mean plus 3 sigma. So if you check that one, actually we can see that that condition is not also not satisfied. Right? So they have seen that when they look at within one standard deviation of the mean, in this particular situation, 86% of the data were there, right? Whereas it should be roughly 68. So there itself, that condition is not satisfied. So that is another reason why the normal distribution is not suitable in this situation. So usually people, as I mentioned, many people, when they see, because as I have mentioned earlier in one day, there are lots of standard theory developed by people for doing different purposes, for different purposes. Most of those theory have been developed assuming that the data are normally distributed, right? So those man-made methods can be applied if you can assume reasonably that the data are normally distributed. And those are the well-known methods available in even elementary books. Right. So when people see this kind of situation, so they check whether they can use a normal model for the original data. So they see that you cannot use it because it doesn't fit a normal distribution. Then naturally what they do is they remove the outliers and see whether you can make it normal. You can make it normal, right? And then after removing the data, they became normal, and therefore this method can be applied and so on. So they write down the paper and publish it. So this is what happens most of the times, right? But that is a completely wrong thing. So therefore, we have to be careful when you are dealing with outliers, right? So some of the key lessons you learned was measurement error is generally equal to measurement error is equal to bias plus a chance error. Bias can be zero sometimes. In that case, we say we have an unbiased measurement, but there can be bias also due to some measurement errors and so on, due to the errors in the measurement equipment, for example. The chance error is a random part. The typical size of the chance error is equal to the standard deviation of the observed data, so you can therefore calculate it, get some idea. Bias is a fixed value. In a given situation it can be plus, in another experiment it can be negative or positive, but in a given situation it is always positive if it is positive, otherwise always negative if it is negative. Bias cannot be calculated, the same as chance error can be calculated, but bias can be estimated, which probably will be discussed sometime later. Right? So all these things can be estimated. Theoretically, of course, we can see in some situations the bias is positive or negative or zero and so on. Right. So that's the end of this section. I think it's a good place to take a small break.